We see here how over the years, and this is running from 89 to 2009, how for the different applications fibers have been installed over the world. You see the large troublesome period we had in 2001, the collapse of the internet bubble. Fortunately, the market was regaining again, and at this moment we are already far above the installed kilometers compared to the 2001 time frame. So you see that we are in 2009 already above 160 million kilometers installed in that year. So that's the level where we are at the moment. You see also the different applications. Certainly important is since 2001, I already mentioned that to you, the growing impact of fiber to the home application. That is the green part. So this particular section is growing very, very fast, particularly in Europe, America, and Asia. You still see that the long distance market is still about stable. Local, so regional and metro is still growing, that you can see from this section. Here you see the same picture, but then more situated to the different areas worldwide. You see here, for instance, that the North American market is losing a little bit on impact. You see the extremely growth in Asia since the 2001 time frame, and in particular Japan, and lately particularly China has installed huge amount of fibers. That is what you can see from these figures. And of course we hope that for you in Africa, we will see a good growth also here in this portion, the upper portion, the rest of the world, that also Africa will need more and more optical cable links and optical fiber installation. And I'm sure that will be visible in the coming years. So you will see that from this domination in Asia, we have seen that over here. Since the started with optical fiber communication, we have already installed more than 1.2 billion fiber kilometers. It is since 19th, I'm sorry. And we see also that the fiber to the home market is growing very, very rapidly. That's an important picture. Another picture is maybe interesting for you if you speak about the choice which kind of fibers. I show you here data of present data and foreseen data for 2015. You see that still G652 CD version is the main installed fiber worldwide, with the AB fiber, the older types over here, and the G655 fibers are a rather limited portion of it, because these are only for the long distance, and you see that the 652 fibers have been installed widely also for long distance applications. So it's, again, it's not a black and white story which fiber should be used for which application, of course. It's clear that 655 will be used for long distance, that's clear. Okay, with this picture I hope to have given you an introduction into chapter 1 on optical fibers. And I hope to have given you some clarifications of all the different important parameters which are associated with optical fibers, and also the different fiber types which we have in our catalog of ITU. And I agree with you, it's not an easy task to make a choice between the different fiber types we have available. It's a balancing act, it's not a black and white picture, and it certainly needs also input from system manufacturers, what they think is the best optimization for a certain link. If there are no questions anymore, I propose we close now, we make a coffee break now, and I hope to see you back at 11 o'clock. Thank you. In chapter 2, we see the following aspects being discussed. We see external factors which are impacting optical cables. We see mechanical and environmental effects on optical fibers. We will discuss general structure of optical fiber cables, structure of optical fiber cables for specific installations, and cable test. And I added in this presentation some additional information which is not in the handbook itself in chapter 2, but for you to accommodate to some references of other recommendations we have in ITU, in particular the series of L recommendations. So the main purpose that we have optical cables is to keep transmission and mechanical strengths of the optical fiber stable in the course of cable manufacturing, installation and operation process. It's clear that a bare fiber is too vulnerable to be installed in the ground or in the air or something like that. You have to protect it against all kinds of effects impacting on the fiber. Now, first of all, I'll show you here section 1 of the chapter 2, which is dealing with the external factors impacting optical cables. They can be in the form of natural external factors like temperature, wind, water, earthquakes. All those are from outside. And we can also have a look on so-called man-made factors which are impacting, like smoke, air pollution, fire, etc. In table 2.1 in your handbook, you see first of all an overview of all kinds of natural external factors which are impacting external cables and internal cables. So you see here a section of a series of different factors, and some of them we will highlight later. You see, for instance, temperature change, very low temperatures for the Nordic countries, wind, salt water, rain and hot spring, snow and ice, water and moisture, sunshine, lightning, earthquakes, etc., conditioning of soil, rodents, birds, insects, hydrogen, water flow, and mold growth, so virgin. Here you see a list of all kinds of typical impacts on a cable, and we see here subcategories of aerial cables, buried cables, duct cables, tunnel cables, underwater cables. And separately we have a category of internal cables, which are customer premises or central office cables. Now I'm not going to highlight all the different aspects. I think you see them in your book. You can have a look what is possible. I can have a look on some of the aspects. For instance, temperature change. It could have an influence on the cable sheath contraction. It can have an increase of optical loss due to high and low temperatures. This is a clear aspect. We can have a look on earthquakes, ground subsidence. Of course, in that case, the sheath could be degraded, impulse, excess strain could be added on the cable. So you see a whole variety of different impacts which are visible and can be acting on the cable. In table 2.2, we see a similar overview. You see the same structure of external and internal cables, but now you see a kind of number of man-made factors. And here you can see, for instance, factory smoke and air pollution, traffic, which are impacting on cables, voltage, which could add and connect to the cable, DC current, impact of petroleum gas leakage, of fire, even nuclear radiation, hydrogen, and installation practices. These are typically not natural causes, but man-made causes which are impacting on cable. And for instance, if we see here, let's have a look on traffic, for instance. If you have a cable which is in contact with traffic, might be possible, then you have a possibility to damage your cable sheath. In table 2.3, you see a more detailed overview how these external and factors, natural causes and man-made causes, are impacting on the fiber itself. And you see, for instance, that a couple of those impacts can have an influence by means of residual fiber strain, which is working out on the strength degradation of the fiber inside the cable. So these are the effects in table 2.3 which are impacting not only of the cable, but inside in the cable on the fiber itself. Effects of, for instance, temperature, which could have an influence on microbending and cause a loss increase, for instance. I have a look on others. For instance, if you have a hydrogen cause created in your cable, it could also be explained and visible by an increase of the attenuation in the fiber. Of course, also many issues like fiber strain are impacting on the fiber breakage, which could have an influence on that. So this gives an overview of all the different causes which are acting or may act on the fiber and the cable, and you should take care of that. Let's walk through them. First of all, let's have a look on residual fiber strain, which is caused by tension, torsion, or bending. And it may shorten the lifetime of the fiber because of increased crack growth. In general, optical fibers, the glass fibers, behave in elastic way up to a few percent elongation before they fall apart, they break. And the strength of the fiber is mainly governed by what we call weak flaws in the fiber, which are already present from production level. And they are always, to a certain percentage, they are present in fibers. Fiber stress will weaken the strength, and certainly when that is combined with a moisture environment to the fiber. And the influence of moisture, weak flaws may grow and reduce the fiber strength over time. Now, we have already seen yesterday that fibers are being tested and in a mechanical way by means of the proof test. Usually this is a proof test level of 1% strain, elongation, or in other units 0.7 gigapascal. This is the minimum mechanical requirement of fibers when leaving the fiber factory. And as I already indicated, in the rest of the fiber lifetime, the permanent stress should be below 20 to 30% of this proof test value in order to guarantee indeed a lifetime of 20 to 40 years. In some applications where you will have a higher fiber strain in your fiber during the lifetime, you will need a higher proof test level. And of course that is possible to reach. It may be at a different cost, of course. A good cable design, and that is very important. Here you see the responsibility of the cabler. A good cable design will limit the long-term strain to safe levels. So again, the whole picture of lifetime guarantee is subdivided over fiber makers, cable makers, and installers. All three, they have a very important responsibility. The other point, 2.2 in your handbook of chapter 2 is saying a few words on impulse fiber strain. This can be caused by impact and snatch during installation and operational life of the cable. When it is exceeding a certain limit, breakage of the fiber is a possibility. For protecting optical fibers, a buffer layer often is used, and further protective layers is added in stranding and sheath construction in order to safeguard them for this impact strain. And armoring, for instance, is one of those protections. Under dynamic stress conditions encountered during installation, the fiber is subjected to a strain from both cable tension and bending. I think that this is important to realize, that if we have strain buildup in the glass fiber, it can be caused by an axial strain because of elongation of the cable, but it can also be caused by bending. If you bend a glass fiber in the outside area, you will induce additional strain to the glass. Both effects can be put together, a summation of both which are acting to the glass, and the strength elements in the cable and the cable bending radius must be selected to limit this combined effect on dynamic strain. So certainly the cable manufacturer will indicate you the minimum bending radius the cable is designed for. Is this clear? Any questions on this part? Okay, then I go to fiber macro bending. Macro bending, we have already seen that in the fiber section, is caused by fiber bending in a cable, and that could be happening because in a cable usually fiber in loose tube or other constructions are stranded together. So there is always a certain amount of bending in the fiber in the cable. And if you add in that also, if the cable is bent, you are adding up the bending effects. Also, an influence is, for instance, the use of cables at lower temperatures. For instance, if a loose tube cable design, the loose tube will shrink more than the fiber is shrinking at low temperatures, and because of that, you get a kind of fiber buckling, additional storage of fiber over lengths in the loose tube, which is causing a macro bending effect because the fiber inside the tube will be at a short bending radius. This may add to the bending issue. But also, of course, a possible sharp cable bending will add to this problem. So bent too small radius is causing macro bending, that's clear. And the cable construction needs a design of bends, a minimum radius of installation cable must be specified. So this is on macro bending. We can also have some attenuation increase caused by micro bending, and that is caused by localized lateral forces, manufacturing and installation strains, as well as dimensional variations in the cable materials due to temperature changes. A cable structure must protect the fiber from lateral forces, and the cable construction should prevent buckling of the fiber during the temperature changes leading to microbending. Because if you have, for instance, a low temperature effect, not only the fiber can buckle and create a bending issue, on macrobending issue, because it's pushed then to the inside wall of the loose tube, you will also have a kind of microbending effect, because you have stresses working out on the fiber. If there are no questions so far, another external impact is water and moisture. Moisture may permeate through the diffusion, and in case of inadequate cable construction or sheath damage, water may penetrate longitudinally within the cable core. So that is a damage which may happen. If fibers are under tensile strength, and if they are in contact then with water or moisture, there's a very good chance then that these weak flows which are in the glass will weaken further and grow, and because of that, failure may happen at a certain time. Now, optical loss may also increase with some cable constructions incorporating metallic elements if there is a generation of hydrogen when water is present in the cable construction. So hydrogen gas will introduce additional losses. We will have a look on that later. Optical fiber should be isolated from water and moisture, particularly in the presence of excessive fiber strain, which is a conclusion from the above. Now, moisture permeation is minimized by longitudinal overlapped and bonded metal foil and the use of water blocking materials. So in this way, we can avoid that water is acting into the cable core where we have the fibers. As an alternative, it's also possible to make a kind of metal tube with the fiber inside, which is a seamless metallic barrier which can be completely effective in preventing permeation. So during the production of that, a foil is formed around the fiber, is welded over the entire length, and then you have a completely hermetic sealing of the fiber inside that metal tube. Of course, you have to take care that, because it's a completely hermetic isolation, that you don't have material inside that tube which are generating hydrogen, because that hydrogen is kept completely inside this metal tube. That should be avoided, of course. Longitudinal water penetration is prevented or minimized either by water blocking materials, which can be used, for instance, in the form of filling compounds or discrete water blocking. So these are the normal precautions a cabler will take care of in his cable design. If we see then hydrogen, hydrogen is an important issue. Hydrogen gas concentration may build up within a cable from, for instance, hydrogen released from the cable components, for instance, from the gel, from the coating materials. Hydrogen may be released over time. Another effect is the electrolytic effects between different metallic elements which are inside the cable in the presence of moisture. Also then hydrogen can be formed and may affect the attenuation of the fiber. Hydrogen could also be contained in pressurized air pumped into the cable. Some cable designs are using this kind of installations, and then it should be avoided that hydrogen is inside that pressurized air. Another cause could be corrosive reaction of metallic elements in the presence of moisture. Also then hydrogen can be generated. And what we will see if hydrogen is inside the optical fiber core, we see that optical loss is increasing, particularly at 1240 nanometer and at the water peak around 1383 nanometer. The 1240 nanometer is a very interesting one because that is an increasing absorption which is inside the glass of the fiber. It is completely reversible. If you have hydrogen coming into the glass, and hydrogen is a very small molecule, can easily penetrate through the glass of the fiber and reach the core, then it will increase in attenuation over there. It's also reversible, I mean with that, if the hydrogen would be released again, is disappearing from the glass, then also the 1240 nanometer peak will disappear again. So it's a good signal. If you have some kind of peak at 1240 nanometer, then you can be sure there is some hydrogen in your cable design. Another effect is that hydrogen can react in a chemical reaction together, and then is forming an additional loss at the water peak. So if you have hydrogen and it's combining then with some molecular structures in the glass, it could create in a permanent loss increase at the water peak. In that case, if the hydrogen is leaving again the fiber, the increase is not decreasing, but this is a permanent aspect of hydrogen. So there are two typical increases: one at 1240 nanometer, which is reducing again if the hydrogen is leaving the cable, and at 1383 nanometer, the water peak, that is a permanent hydrogen increase. You cannot get rid of it anymore. So, any questions on the effect of hydrogen in a cable? Okay, I continue then also with the materials to be used in a cable construction. Should be selected so that the concentration of hydrogen within the cable is low enough to ensure long-term increase of optical loss. So that is, you have to take care, a cabler has to take care on the components and the materials he is using in the cable design, the materials around in the cable, the sheaths, but certainly also, for instance, in the gel and the loose tubes. As an alternative, hydrogen absorbing materials or a dynamic gas pressurization can be used to eliminate or reduce the added loss due to hydrogen. So there are ways to fight against the hydrogen formation, for instance, by these absorbing materials. The concentration of hydrogen within the cable core could be estimated from knowledge of the hydrogen released from components of the cable, and there is a particular recommendation in ITU L27 which describes some more about testing this phenomena. Okay, then we have another contribution we should take care of if we speak about external factors, which could be lightning. In particular, if we have a construction of the optical cable built up with metallic elements, then such a cable has a greater susceptibility to be struck by lightning than cables without metallic elements. I think that's clear. Lightning impact causes a current to flow in the cables. The mechanical impact and the energy dissipated from the lightning strike may damage the sheath and also the fibers inside the cable. So there is a real danger in that case. To prevent or to minimize lightning damage, construction may be considered of non-metallic cables, because then the sensitivity of such a cable is lower. High current carrying sheaths, there's also a possibility to take care of this, or alternatively, some methods proposed in ITU recommendation K25. I have not looked into this recommendation, but you can look for it and download it from the website. So these are some issues around the possibility of lightning in your cable. Nuclear radiation, that is maybe an issue which is not happening so often. Optical fiber cables may be exposed to nuclear radiation, causing optical loss, increasing to an unacceptable level. We call this loss radiation-induced attenuation. Normally, we see this effect in particular for cables inside nuclear environments, like nuclear power plants. If we have a cable inside a plant and radiation is present, that radiation may give a certain damage to the glass, because of which the attenuation of the glass will increase. Considerations on the cable is still under study, so we will not see this effect so often in normal applications. For those applications where we have cables necessary in a nuclear environment, so for instance for nuclear power plants, special fibers have been developed and are available. These fibers are not specified in ITU, but several fiber makers make them available. Another external factor could be induced voltage, which is a man-made effect. Under some fault conditions of electricity lines, optical fiber cables containing metal elements are susceptible to induced voltages, and that could reach, of course, magnitudes damaging the cable, but also causing a safety hazard for the personnel handling the cable. So this is an issue to take care of, particularly for the human aspect. To prevent or to minimize the effect due to induced voltages, there is a directive from ITU, a directive concerning the protection of telecommunication lines against harmful effects from electricity lines, and that should be taken into account. Okay. Another external factor could be biological attacks on the cable. The outside of a cable can be damaged from biological attacks, for instance by mammals, squirrels, mice, rats, moles, and other rodents. I think that is well known. Also birds like the woodpecker, cockatoos, insects like termites, ants, beetles, wasps, and also microorganisms like bacteria, fungus, and molds could attack the cable sheaths. When it is not possible to reside the optical cable, one could eliminate this hinder using chemicals or poisons. However, we should care that in this case, these chemicals and poisons are useful for sometimes, but they can be a danger for human beings and also cause environmental pollution. So there is a certain limitation in using this kind of contradiction elements. Some chemicals are useful as a deterrent, so to get rid of the attacker, not as a poison, but just to frighten them off. Some chemicals are sprayed on the cable structure, on the surface, and they leave a special smell as a deterrent. Another option is to shield the plant using protective materials around it in order to prevent access. And cables with sheaths of lead, polyethylene, polyvinyl chloride, neoprene, and other polymers are all susceptible to attacks. Cables with steel armoring and dielectric armoring, such as fiberglass or both, do not suffer any damage of this type as long as the armor is intact. But of course, this will have an impact on the cost price of a cable in that case. It gives you some idea about the different strategies you could go for in eliminating the effects from biological attacks. Any questions so far? Okay, then we go to a next section of chapter 2, in which we will talk about the general structure of optical fiber cables. We can recognize main cable components as the following. That is, of course, the optical fiber and optical fiber coatings. We can have a look on the cable core of the cable, the strength members inside the cable, water blocking materials, if available, the sheath materials. So we will walk through these elements one by one. And in general, these all contribute to the generally applied in optical cables installed in ducts, tunnels, and bridges, and are described in ITU recommendation L10, or indirectly buried in the ground, as we can see in recommendation L43. So let's first have a look on factors affecting the choice of cable components. This is table 2.4. You can find it also in the handbook. And it's indicating mechanical and environmental factors affecting the choice of the cable components. We see here again on the left hand some mechanical and environmental factors like residual fiber strain, we have discussed them all, impulsive strain, macro micro bending, water, moisture, hydrogen, lightning, and nuclear radiation. And then we see here on these columns the effect on coated optical fibers, the effect on the cable core, the effect on the strength member, water blocking materials, and sheath parameters. In two categories, we have a category A, which is a primary factor in that case, or a secondary factor. And you will see that, for instance, all those mechanical aspects like fiber strain is of prime importance for the aspect of fibers and on the cable core. Strain has a lower impact on the sheath materials. We see also that macro and micro bending and also water also have a high impact on the optical fiber, and partly, like here, micro bending partly because of the sheath. Macro bending, on the contrary, there we have an impact also on the sheath making. For instance, effects like moisture and hydrogen, these are not impacting directly the fiber itself. These are of secondary choice. Of course, if we have a look on lightning, then the strength member, which can be a metallic element, and also the sheath material is of importance in that case. So it gives you an overview of what kind of effects are working out on the different components of the cable. Now, the optical fiber itself, we have seen already the base form of a fiber is in primary coated optical fiber. I've indicated here with the cladding in dark blue. You see here the core inside, the single mode core. And then you see that two layers are around the glass, a primary, the inner layer coating, and the primary outer layer. So in the fiber production, we have added in two layers of coating, and these are indicated as inner and outer layer. Now, first of all, the goal of a primary coated fiber is to have protection to the glass. That is the main importance of a coating. It's added during fiber drawing. I explained that to you yesterday. Usually it is a curable UV acrylate. In some cases we can also go to other materials, for instance, if high temperature coatings are needed, but normally for normal use in telecommunication, UV acrylates are used as coating material. As I explained yesterday, we use often dual layer types to minimize microbending sensitivity, which means in general that we have a soft inner layer directly in contact with the glass of the fiber and a hard outer layer to protect the whole assembly from the cool outside world, so to say. It's specified for a certain temperature, usually that is for fiber at least minus 60 degrees up to plus 85 degrees. But as I explained, we have also special coatings available if we have to apply this fiber to another temperature region. For instance, high temperature coatings are available up to 200 or even 300 degrees for very special applications. In general, the requirement is that the coating should be easily removable. So when we make splices, we have to be able to get rid of this short piece of coating, so stripping is important. Often for fiber identification, if you have multiple fibers inside a loose tube, you have to recognize these fibers. A coloring scheme is used. This can be added as an additional layer after fiber drawing. In some cases, it can also be integrated in the primary outer layer, a feature we are using in my factory. In addition, we can use the same color by adding multiple ring marking on it, and in this way we can use, for instance, a color red multiple times. We can add a kind of ring marking on the color layer. We can give it 1 ring or 2 rings or 3 rings, and then we can use the same color red 3 times inside the same tube for recognition purposes. So this is another possibility to increase the recognition of the fiber. And of course, all these fibers have to fulfill one of the G65X recommendations. Now, secondary coated fibers can be in different forms. We can have them in the form of a loose packaging within a tube or a groove. I'll explain that later. We can also have that in a kind of micro-module construction. We can also have it in a tight jacket coating. And a special form of that is also a ribbon construction. First example is a loose tube. Here you see a plastic material, a plastic tube is formed, and with the fibers inside that. Here you have the primary coated fibers. Inside the tube we can either have, usually we have a filling compound, a gel, but there are also cable constructions without the gel. Another example of a loose construction is what we call a slotted core construction. You have here a plastic form in which you have a kind of grooves, and in these grooves the fiber can be laid down during the making of the cable. Special care should be taken by the cabler that if you have fibers inside this construction, either loose tube or the slotted core, that you should have a certain overlength of the fiber inside the tube. Because if you later are going to strand those tubes along a strength member, then you have this construction, those multiple tubes are surrounding the cable and make a kind of helical formation. The fiber should be at normal temperature in the middle of this tube. And the design of the cable should be in such a way that if the cable is being installed and elongated, that the fiber, the fiber will move to the inside of the tube, because you are going to elongate the whole cable under certain conditions. In that case, the fiber should be free to move from the center position more or less to the outer dimension, but the cable should be designed in such a way that from this point on, no additional strength and strain should be acting on the fiber. So this is a cable design factor. On the other hand, if you have an installed cable which is going to be used at low temperatures, then the whole construction will shrink under the influence of low temperatures, and then the fiber will move to the outer part of the tube. Also, that needs to be a design criterion for the cable, that this is not an overreaction, that the fiber is not going to start buckling inside the tube. I mentioned that already as one of the factors in which attenuation could increase: low temperatures, fiber buckling in a tube. So this is also a criterion for the cable maker designing the tube and the overlengths of the fiber in that tube, making care also of the final cable construction. The same is happening also for fibers in this slotted core. Normally the fiber should be, let's say, in the middle positions. At installation, when the cable can be elongated, the fiber should, as a maximum, enter the wall of this tube, but not more than that. It should not build up strain in that position. And at low temperature, when the whole construction is going to shrink, the fiber will move to the outside region, but not further than indicated over here, because otherwise macro and possibly micro bending effects are starting up. So again, this is a construction, a design criterion of the cabler. Is this clear for you, that there are constraints and issues around the cable design to have it being worked out well? So this is certainly the responsibility of a cabler. Yeah.
Thank you. Suppose that between the tubes, if there is a high humidity and there is some water, it is not. It can't. What is the effect of that humidity if you have it in between the two tubes, or between tubes?
Well, in general, water will not go further into the tube. If there is any leakage because of damage, maybe that water comes into the tube, and generally the tubes are filled with a kind of gel, also protecting that water and humidity goes further into the cable. There was another question over there.
Thank you. I didn't quite understand the different positions of the fiber inside the tube. It seems that these positions depend on the environment and the situation you're in. That is it to mean that the tube is empty? I mean, is there anything around the fiber that can maintain it in a position, in a certain position, or is the fiber free to move into different positions?
Thank you. Yes, a good question. Yes, the fibers should be free to move inside this tube and act on those environmental conditions, either in cable strain or in low temperature. So it should be able for the fibers to move a little bit in this range. For doing so, during the cable production, the loose tube production, the fiber should have a certain overlength compared to the tube, because later when the tubes are stranded around the strength member, the final position will be reached. And then this overlength is exactly compensated and should give a fiber position roughly in the middle of the tube. Any more questions? Another construction is what is called micro module, which is indicated over here. You see here that fibers are in a very compact structure with a thin wall of plastic material, tubing wall around it. And what you can see that in this kind of constructions, cables can be made, especially for fiber to the home market, which are very compact. So all those micro module elements can be packed together. And what you can see is that in this case, the strength member, which is usually in the center of the cable core, is taken out and placed in the jacket materials. In this way, we can make very compact cables. And as I said before, this kind of cables have especially been designed for fiber to the home applications. Possibilities are shown over here in outdoor or in indoor constructions, or for multi-purpose constructions with more metal materials for improving the strength. Then we have a tight secondary construction. So far we have seen loose construction where the fiber is not in direct contact with the secondary coating. This is here differently. Here we see that the secondary coating is in direct contact with the primary coating of the fiber. So we have a direct secondary coating on top of the primary. So in the center we have the glass fiber with its primary coatings, the red and the green one, and surrounding that we could add a buffer material if necessary. You can also leave it out and immediately put your secondary coating around it. So this is clearly a different structure compared to loose constructions. A very special form of tight contact is the ribbon cable. Here you see that a couple of fibers are placed next to each other, and there is a coating matrix around that, which is the secondary coating material. You see it is in direct contact with the primary coating of the fibers. The development of ribbons has been come from the idea that in this way you can improve the speed of installations. Because normally if you have this kind of cables, splicing of such cables does not need to be on an individual base anymore, which is the case if you have loose cables. Then each individual fiber should be spliced to the next following fiber in the next following cable segment. In this case, you can do the splicing in one run. You can take off the coating material, the matrix material. You can cut the fibers and cleave it in one handling action, so all the fiber ends are at the same position, and then you can splice two of those elements to each other, and meaning that you can splice in one run 4, 8, or 12 of these fibers, or how the ribbon is built up. So main purpose is to improve the speed of installation. That is the background why this kind of ribbon constructions have been developed. Of course, you need different splice machinery for this kind of applications compared to single fiber splicing, which is done for loose tube applications. A special form I showed here, what is called encapsulated ribbon, in which you have the coating material completely surrounding all those individual fibers. There are also ribbons called edge bonding, in which we have coating materials, additional coating material in between the fibers and not surrounding the whole structure, or like here. The most often used construction of ribbon is the encapsulated structure. Typical developments of this construction are, for instance, in Asia, Japan, a lot of ribbon cables have been developed. In the United States, you see often this kind of developments. In Europe, it is a bit limited. You see some countries who have been chosen for this solution. For instance, Sweden is using quite a lot of ribbon constructions, while in most of the other European countries, all have decided to go for loose tube cables. Any questions on this particular construction? Okay. Then we move to the cable core, which is described in section 3.2 of your handbook. The core of an optical fiber cable is usually formed by using one or more optical fiber units. The number of fibers in the cable and the type of application will determine what kind of optical fiber unit structure is selected. It's also important to take the cable installation and fiber jointing into consideration if you are discussing this. And in the next graph, the quality is not so good, but you can see a more clear example in your handbook. You see here a kind of overview for single unit cables. And the single unit is built up out of three possible structures. You see a single tube construction, a layer construction, of a slotted core construction. So in the loose packaging, you can see here for the tube construction, different fibers can be inside that tube, can also be tight, secondary tight coated fibers, which are in this tube construction, or even a ribbon construction could be inside this tube. In a layered construction, you see here that multiple units are available in which the fiber is present, and in the case of tight buffered construction, you see in that case that tight buffered fibers are placed inside this construction. Here you see for a slotted core construction again different loose packaging. You can see it again here in this example. And in the ribbon application, you see that packages of ribbons can be placed in this slotted cores. Again, I think you can have a clear view in your handbook what are the different applications. Of course, you can also go to multiple unit cables. And in this case, you see here the most used form is, for instance, this loose tube cable, in which you have a couple of tubes which are surrounding a strings member. So there's a cable stranding process in which all the different tubes are placed around a strings member, and each tube contains a number of fibers inside this tube. It could also be a tight buffered construction together, which is forming one unit, and then multiple of these units are then combined into the final cable. Similarly, you see here a microstructure construction. Multiple of these units can be combined together, forming such a microstructure cable. And here, for instance, you see the different ribbons which can be placed in a slotted core construction, and each element can be repeated a couple of times. So you see the use of multiple unit cables. I think more clear pictures are inside your handbook there. Going a little bit more in detail on the cable core structure, paragraph 3.2.3 is describing some of the water blocking materials. The goal is to protect fibers from the ingress of water and moisture. That was already your question.
Yeah, I want to just go back a little bit about that figure on multiple unit cable construction. Is there any standard on the, because there you can see you have many tubes, and inside the tube, one tube you have many fibers. Is there any standard about the colors of fibers and colors of tubes, which is international standard?
No, officially there is no official standard on the coloring. ITU, neither ISC has been describing the particular coloring schemes. There are different schemes going around on the world. Unfortunately, there has never been a possibility to have a standardization on that due to commercial aspects maybe of different cablers and manufacturers. But indeed, there is no official coloring standard. You see them sometimes in regional specifications, if I'm right, but don't give me wrong if I'm wrong. I believe in North America there is a coloring scheme, but such a coloring scheme has never been accepted worldwide, so to say. So there may be regional accepted coloring schemes, but not a general one accepted by ITU or ISC. Okay?
Just a precision, can you tell us what's the use of the electrical radial strength on the side? What's the purpose? What is it used for in this kind of cable?
As I explained just a moment ago, these kind of cables are particularly used for very compact cables because the strength member has been replaced from the center part and replaced to the outside part, so the fibers can be joined very close together. They are very close together. If we still would have the strength member in the center part, that would cause additional microbending on the fibers. So the strength member has been removed from the center part, which is the usual construction, as you can see over here. That is the standard construction. The strength member has been replaced to the jacket material, and in that case, the fibers do not touch them anymore. So you can place those cable units or fiber units very close together. Yep. Again, building very compact cables. Yeah. Good questions. Any more questions on this subject? Okay, then the issue of water blocking materials. Again, the goal is to protect that fiber is transporting inside such a tube, so it should protect the ingress of water and moisture. And examples are, for instance, the filling compound. That is one of the gels which you can put inside a loose tube, for instance, surrounding the fibers. You can also use a swelling tape around a stranded construction. Along your strength member, you have stranded all those different loose tubes, and then you can surround that with a swelling tape. So if there is any water coming through the sheaths, the tape will swell under the influence of water and block further ingress of water. Another example is to use swelling powder, same performance, or a combination of these materials. It's all intended to avoid that water is coming into the core, the central core containing the fiber. We should try to avoid that water is very near to the glass of the fiber. That is the background. So a filling compound or a swelling powder is distributed into the interstices of the optical fiber unit and the cable core. The filling compound can also be used as a filler of the tube and the groove. So that's the slight difference. You can filling compounds you can place inside the tube, while the powder and the tapes are outside the tubes. As said before, swelling tape is usually wrapped around the optical fiber units or the cable core. Now the important points of filling compounds and swelling tape and powder is the following. It should not hinder the movement of the fiber inside, for instance, the loose tube. We have seen already that the fiber must be able to walk a little bit through its position in the tube, and the swelling and the gel inside the tube should not prohibit that. So the fiber should be able to make still some movement in the tube. Compatibility with primary coating and coloring materials, so there should not be a worse interaction between gels and the coating materials of the fiber. There should not be a change of optical performance when activation of water blocking materials. There should be no change in the optical performance with temperature variation. It should be easily removable when splicing. If you are opening a cable for making splices, the materials for this water blocking should be easily removed in order to have an easy installation practice. Now, options for longitudinal water tightness of the optical fiber cable are the following: a continuous blocking or discrete blocking, so that you repeat it at certain positions and not continuously. So that's the difference between the two solutions. In this solution, for instance, you have gel all over the whole tube. In other positions like discrete blocking, you repeat it only at certain positions and not over the complete length. An important aspect is hydrogen. Hydrogen absorbing chemicals may also be introduced into the filling compounds applied to the interstices of the cable core. In case of unacceptable high concentration of hydrogen be predicted within the cable during its lifetime. So there can be materials which can absorb the generated hydrogen coming out of the materials, can be absorbed, because also here hydrogen should be avoided coming near to the glass. Alternatively, the cable construction can be such as to minimize the generation of hydrogen. That's of course already a first step to overcome problems with hydrogen. So modern coatings nowadays have a very, very low hydrogen generation, and we are looking to that as fiber makers, that is kept on a very, very low level. Another aspect of the cable core, you find it in section 3.3, is concerning strength members. These should be designed in such a way and estimating the required load on the cable, taking into account, of course, the cable weight, the cable design, the range of the temperatures in which the cable is being used, and the conditions of installation. There can be a variety of cable installations, as we will see tomorrow when we deal with Chapter 3, cable installation. Ensuring the fiber are not strained beyond a certain maximum limit, taking into account the dynamic strain induced during handling of the cable. So we should know to which strains the cable is acting on during the cable installation. Under maximum loading, strength members should remain elastic, ensuring that after the cable has been relaxed again, the fibers are still maintained and keep the permissible long-term residual strain. If we have, for instance, a situation that the cable is loaded over its maximum level, the strength members could be elongated and not relax anymore completely. And that could mean that the fiber then keep their strain over a long time. And that could be the case that we reduce the strength guarantee of the fibers. So this is, again, an item for installers and also in the cable design that we clearly understand to which maximum load the cable is worked on. Installation requirements may determine the strength members location. It can be a cable preparation and fiber splicing. How easy is it to work with the strength member? The sheath jointing, cable pulling devices, and the cable size. They all have a certain impact on the choice of the strength member. Looking to the cable sheath and the armoring, the cable sheath in the end protects the cable core from mechanical and environmental damage. That is the outer part of the cable. Characteristics to which should be considered in choosing the sheath is hydrogen generation, climatic performance, the air tightness, moisture penetration and the resistance to that, mechanical stability like bending effects, torsion, radial pressure, tension, abrasion, chemical resistance, the diameter of the cable, the weight, and the fire resistance. So these are all elements which deal with choosing the correct sheath material and the sheath construction.